G'day, I'm Glenn Morris from the Smart Energy Lab, and today in the lab I've got Peter Sykes from Rectifier Technologies. Hey Peter, good to see you.
Hi Glenn, thanks for having me. It's great to be at Smart Energy Lab again.
How was that drive up the hill in your EV?
After I had the heads up about people getting here with not much battery charge left, I made sure that I had plenty, and so it was really beautiful and stress-free. It's good.
Yeah, we've had a few near misses and one where they had to turn around, go back to Healesville and top up again.
I wanted to make sure that wasn't me. So, no, it was good.
Great.
Yeah.
Now,
and it's a beautiful spot here.
Yeah, it is, isn't it?
Yes.
So, Peter, we've known each other a long time, and we've got a mutual friend going back to when you were at university.
Yes.
So I reached out to her today and I said, tell me some fun facts about Peter from his university days.
Right.
And she said, nothing that your audience could hear. So I don't know what that meant.
Thank you. That's very, very gracious. University was a fun time.
Yeah.
I'll leave it at that.
So, for all those people looking for career choices, what did you choose?
I had an interesting time. So when I was at high school, I was studying essentially maths and sciences, and I thought engineering was interesting, but I liked just the blue sky nature of science, where you can just study something for its own sake. And so I remember going to the Monash Uni Open Day and coming back and explaining to the careers counsellor at school I was really excited because I discovered that there was a double degree. You could do a science and engineering degree. And so I didn't need to choose. So I could just go and still do both. So that led to a long time at university. I spent the maximum time that I could at university and came out with a science degree and an engineering degree. And all the time that I was studying engineering, I just couldn't imagine that I would have a job where someone was going to pay me to design things that they would then go and build. And yet, lo and behold, that's exactly what I'm doing now. And it's been really exciting and fun. Right.
So power electronics, that was your passion?
So my dad studied electrical engineering and did a PhD in electrical engineering. And so at home in our shed when I was growing up, we had these racks of equipment that you would probably describe as an analog computer. And essentially I just pulled them all apart. And so I was interested in that. And then, power electronics grabbed to me because it really covers, you have to be across the whole breadth of electrical engineering to do power electronics engineering. There's, thermal management, mechanical arrangements, design of magnetic components, circuit topologies, control theory, digital control, and you've got to, I'm not an expert in all of those things, but you have to have a broad understanding of a lot of different technologies to be able to make a piece of power electronics work.
Right, yeah. You've got to have that overview.
Yeah.
And focus in on your speciality, but keep your heads up on where other people might slot in.
Yeah, get an effective team and be able to work together with that team to get a good outcome.
So that kind of brings us to Rectifier Technologies. I'm just guessing it has something to do with rectifiers?
Correct, that is it. So it goes back to the days when, for telecommunications exchanges, that they were run off 48-volt batteries because they needed the backup if the power went out. And so the bit of equipment that charged the battery was called a rectifier. And historically that would have been a diode bridge and a capacitor rectifier type of thing. And then where Rectifier Technologies really got started was they developed switch mode converter technology for telecommunications rectifiers. And they were very successful at that. And then they expanded into sort of that utility backup space. So, we have clients who might run substations and they need backup power for the control systems in their substations. And so we're providing the rectifiers that keep the batteries charged for for that backup.
Just to explain to our audience a bit about the difference between switch mode and, say, a bridge rectifier with a transformer.
So in a transformer with a bridge rectifier, all the power conversion's happening at mains frequency, which is in Australia is 50 hertz. when we use switch mode technology, we use power semiconductors to do that power conversion at much higher frequency. So, for example, it might be typically 50 kilohertz or 100 kilohertz even.
So you're bringing in AC, rectifying it to DC.
Initially, yes, there would have been a conventional diode rectifier,
Yep.
and then you would use switch mode technology to process the power after that. These days, we're doing the direct interface to the grid is a switch mode converter.
Right.
And so hence that's where your EMI filter becomes much harder to do. Well, it's more important to have a good EMI filter.
Yeah. I'd love to
yes.
expand a few acronyms for our audience.
Sure. EMI, electromagnetic interference.
Aha, had to think about it.
Yeah, or other people use EMC, which is electromagnetic compatibility.
Yeah, because there's regulations around it.
Yes.
Yeah.
So I describe the way I describe what electromagnetic compatibility is you remember in the old days where you had the kitchen whiz,
Yeah.
right? And when you turned on the kitchen whiz, the TV just went to snow,
Yeah.
right? And so what that means is that the kitchen whiz is radiating too much, and the TV is too susceptible to that radiation, and so or that interference.
Would that be a brushed motor or? What was it
Yeah,
causing
possibly, yes.
Yeah.
Yeah.
So lots of arcing and
lots
sparking.
of arcing and sparking. and so it can be actual radiation or it can be conducted in the power lines.
Yeah.
It can be both. And so essentially electromagnetic compatibility means you have to design your equipment so that it is not susceptible to other emissions made by other equipment. And so the limit for that will be up here, and then the emissions limit is set down here so that other equipment shouldn't emit noise above a certain level, and there's a margin in between, which means all the equipment can operate compatibly with each other.
So this is the challenge for Rectifier Technologies, is to build something that's efficient, but doesn't generate lots of electromagnetic noise.
Correct.
Yeah.
Yes.
And that's what you've done.
Yes.
How long have you been doing this for? Rectifier Technologies.
So Rectifier Technologies this year celebrating their 30th year, which is a great milestone. Their business has evolved from initially being a licensing business where they would develop technology and then license it to other people. We now own our own factory and are manufacturing equipment for our customers.
So 30 years ago, what was the market?
Well, the market was telecommunications companies that needed to keep all those exchanges going and have backup power for all those exchanges.
Are you still doing that?
We still do that for some customers. It's mostly, I would say now, we do the backup power for industrial applications. So it may be, a substation either for a power utility or a substation for a mining company where they've got a remote area, power system. We also do some scientific instrumentation power supplies. So they're high voltage power supplies for companies that make sort of spectrometer type equipment. So they have a very particular requirement, and yes, we've developed and manufactured power supplies for them.
So basically anywhere that someone needs DC at different voltage levels and power
Correct.
levels,
Yes.
taking in AC as a source.
Yes.
Yeah, right.
Yeah. Historically, that tended to be single phase AC.
Yep.
And now, as the power levels are increasing, obviously we're moving to we have been doing for a while, three phase, taking in three phase AC.
What's the advantage of doing it via three phase?
So, for the same amount of power, you are going to draw a lot less current. So, in the first instance, a third of the current, because there's three phases, and the power flow. So with a single phase, you can't get away from the fact that it's a sinusoid, and you're drawing a sinusoidal current out of a sinusoidal voltage source. So the power must be sinusoidal. And so that means you need a greater energy storage capacitor within your equipment to smooth out that sinusoidal power flow.
And you're going through zero.
Zero. Every
100 times a second.
100 times a second, you're going through zero. Whereas with three phase, inherently, it's much closer to DC. The power you're drawing from the grid is never zero.
Yeah.
right? Because at least from one of the phases or two of the phases at a time, there's a non-zero power coming in.
Yeah, you're sort of overlapping.
Yes.
Yeah.
Yeah.
I was trying to think of an analogy just on the fly, and I couldn't think of one. But I was imagining people rowing, like all pulling together.
Yeah,
so there's a pause and there's another pause. Imagine if we rowed in three-phase at 120 degrees apart.
Yes, it'd be like that.
Everyone has a slightly different pull cycle.
Yeah.
You get a very smooth flow on the water,
You
though.
do, yes.
That will be the difference. You
Yes.
wouldn't be going zip, zip.
Yes.
And that's one of the problems
and
with
so
single phase.
especially for where it's really advantageous is for motors,
Yeah,
right? There's just a steady power flow.
yeah.
So that has advantages of not wearing out bearings and things like that in motors.
Yeah, vibration.
Yeah. Yes, that
and
sort of stuff.
speed change.
Yeah.
What about split phase? That bizarre thing. Do you do anything in that
No,
in that
we
space?
don't.
No, it's just a bad idea.
Yes. Yeah. I mean, yes. But this is one of the advantages of power electronics is it does make so it does really make it possible to develop a single piece of equipment that you can put into any market in the world, whether they're 50 hertz, 60 hertz, whether they're 120 volts, whether they're 240 volts. You can just make one piece of equipment that can automatically adjust and regulate and take the power from whatever is presented to it.
Which is what we expect of every plug-in, device we have now.
Your iPhone charger. It's the one other than the little prongs coming out the back.
Yes.
What's inside it
Naughty
is this.
people sometimes bend.
Yes.
To get them in the PowerPoint.
Yes.
Yeah.
Well, they shouldn't do that.
No, it shouldn't. It's dangerous.
It's dangerous.
Because you don't get proper mating, do you?
Yes. But what's inside the little box is the same all around the world.
Yeah. So coming back to Rectifier Technologies, where are you based?
So our design centre where I work is in Burwood in Melbourne in Victoria. Our sales and marketing group are based in Singapore, and our factory is based in Johor Bahru in Malaysia.
Wow, so global company.
A global company,
Wow.
yes.
Ha. And
A multinational.
I've got some notes here, which is a bit of Dorothy Dix, because some of these were provided by your team, but
Yes.
I note that you've received an award from the Victorian government. What was that for?
We have. It's called the I Awards. They're an innovation award it's a competition run by the Victorian government to highlight and bring to people's attention the exciting things that are going on here in Victoria in technology development.
So you won this award from the Victorian government, the I
Awards.
Award. What was it for?
So that was for our RT22 EV charging module, which is a 50 kilowatt charging module. It takes in three-phase AC and provides an isolated, regulated DC output current for charging electric vehicles. And that voltage can be anywhere from 50 to 1,000 volts, so it can do all of the Char Demo or CCS range.
Wow. 50 to 1,000 volts. Insane range.
Yes.
Right. And
Yes.
what sort of current?
So at up to 400 volts, it'll do 125 amps. And then above that, the current decreases to maintain its 50 kilowatt rating. So a 50 amps at 1,000 volts.
So at 50 volts, how many amps can it do?
Still only 125.
Okay, yeah, I was going to say that
so
wouldn't go
below,
up.
it can only deliver its full power down to 400 volts.
Yeah, I get
And then
you.
below that, the power decreases because we're at the maximum current that we can deliver.
Now, if anyone's wondering, we actually got an RT22 in the boot of
boot.
Peter's car. We'll bring it out and do the little reveal, but it's coming, so just hang in there.
Yeah.
So we're moving on to EV charging now. How did Rectifier Technologies go from making charging unit for telco sites to EVs?
So what was happening was that battery voltages were increasing, and so we had people coming to us saying, "Can you make a charger that can charge 400 volts?" And then we had people coming to us who said, can we use these modules in an EV charger? And so we started selling those modules that hadn't initially been designed as an EV charging module to companies that wanted to make an EV charger, and they were putting those modules inside it. And then as we looked into it further, we better understood what an EV charger was. And so we've also now are developing our own SECC, which is Supply Equipment Charge Controller, which goes inside your EVSE, your electric vehicle supply equipment. And So we're doing that as well. But that led us to really then focus on what would be a module that would be really suited to an EV charger.
Gotcha. I'm just going to stop you there for a moment because we've run through a few acronyms and descriptions. Just for the audience, when we talk about chargers, we're actually talking about a DC charger that's directly charging the battery in your car. The thing that most people refer to as a charger is actually just electric vehicle supply equipment. It's a box on the wall, single phase or three phase AC power that plugs into the car and communicates with the car. The car itself determines the charge rate. So for most people at home, they'll be charging with either a plug that plugs into a 10 amp socket or a dedicated EVSE, if in the latter case it'll be the vehicle that determines the charge rate. So just because you bought a 22 kilowatt EVSE doesn't mean it's going to charge your car at 22 kilowatts. Yeah. But DC, it's a whole different story.
Well, it's still the car telling the equipment how much current it wants, and then the equipment just provides that amount of current. So the car is always monitoring, because the car is in control of the battery, and it's things like battery temperature, battery age, all of those things state of charge, all of those things determine what's the best rate to charge that battery at to give it its maximum lifetime. And so the car's carrying the battery's part of the car chooses how fast to charge the battery.
I've had people say to me, it's not good to use your DC charger to charge your car. You should be using the AC supply.
What's actually happening is the AC is being converted to DC. It's just the car either has an onboard charger that is converting that AC to DC. Electric vehicle charger that's outside is converting the AC to DC. A battery can only be charged with DC power.
I think they're referring to the rate of charge too, because generally DC chargers are much faster than your wall-mounted AC supply.
And so that's really where people need to think about that. The electric vehicle maker has determined what is an appropriate level to charge that battery at. They're providing the warranty on that battery, and so they've determined that it's okay to charge that battery at that rate.
Right.
So it's the car that's making that decision.
Yeah. I've noticed that because we've got like 7 EVs here, and people plug them in all the time, and they charge at different rates because of temperature, the condition of the battery, the state of charge. It's all because the car is looking after that battery, and that's covered by the manufacturer's warranty and the design of the product. So you can feel confident that you can use a fast DC charger because it's warranted for it.
Yes.
Okay.
Yes.
Yeah, it's also, what people want. They don't want to sit around for 8 hours watching it slowly fill up.
I think it actually, it kind of depends. And for some people, there will be a bit of a paradigm shift in the context of essentially wherever they are, wherever they're sitting down, they will plug in their mobile phone so that it's just always charged. And similarly, there are people who I speak to who say you've just got to make a bit of a shift to that mindset that essentially wherever you are with your EV, if it's parked somewhere, wherever you possibly can, you're plugging it in to charge it up. And so then if you're in that mindset, the actual charge rate becomes less important. Where the charge rate is important is where people still have the mindset of I'm going up to a petrol pump and I want to spend 3 minutes filling my petrol tank and then I go again. Right? In that mindset, then the rate of charge is very important.
Yeah. So
it's all about the rate of charge.
If you're travelling, that's important.
That's important.
Yeah.
Yes.
But if you're at home, it's not important.
It's not important.
Yeah. If it fills up in 10 minutes or 10 hours and you're asleep, it doesn't really make any difference.
Yes. And we're seeing these things. The market is evolving and different trends and patterns are happening. We've done some work on a DC charger for home use that's a 7 kilowatt single phase or an 11 kilowatt three phase charger.
Whoa. Did you say DC home charger?
DC home chargers.
That's a new one on me. Wow.
Well, so we've done some development on that.
Yeah.
And what we're now seeing is, and us and we know other companies as well, are struggling to actually see how it's going to work in the sense of who's going to buy them, right? Because all the cars are still carrying around their own onboard charger. We're not yet aware of a car that doesn't have an onboard charger. So it would only when an electric vehicle maker decides to not have an onboard charger anymore, then we can see there'll be a really big market for a home DC charger that can charge more quickly. But until that happens, well, people can just still plug into a plug at home. And so why would they spend the money to get a home charger? And so, we've done some development in that area. We know other companies have as well. But it's just, a few years ago, it was looking like that decision might be made more quickly. It hasn't been yet. And it'll be, I'm sure the car makers are all sort of looking at each other going, right, who's going to be first?
Cars are really interesting the way they've evolved, what the product offers. I'm just thinking back, my first car, it's embarrassing, was a Lada. Russian-built Lada.
Wow, fantastic. I wouldn't be embarrassed about that. Oh, that'd be cool.
Well, it was a pretty clunky car. Put the indicators on and
there weren't many else.
The horn would go off or whatever.
Yeah.
But also, it came with a tool bag that you could do engine maintenance on. Basically, it was like a golf bag full of tools, right?
Yes.
Now, these days, you're lucky if you get a wheel brace.
Yes.
Also, you're lucky if you get a spare tyre.
That's right.
Because it's extra space it takes up in the vehicle, so that you're actually interested in volume for storage, and it's an extra cost, and you hardly ever use it.
Yes. So I don't have an EV yet, but I've got a hybrid.
Yep.
And we went on a trip to Alice Springs, and so for that I had to go and buy a spare wheel that sits in the back of the car because it didn't come with a spare tyre. And because I was going to Alice Springs, I thought I probably should have a proper spare wheel.
Right. Yeah. I think Apple has started doing that in a big way too. Like, you don't even get a plug pack now with the phone. All you do is get the cable.
Right. Okay. Yes. Well, and partly that's just those little outlets. They're ubiquitous.
Yeah, that's right.
And I think, in the longer term, that's where I see EV charging will be. Just wherever you are, there will be something for you to plug your car into.
So what would be the advantage of a DC home charger over a conventional EVSE?
From the car side, it means that the car's not carrying around the weight of an onboard charger. So, and that would enable then the car to be cheaper. So it's about where you put the cost.
Aren't you also allowing for more choice about rate of charge? Because the onboard charger is a fixed charger. You can't change it to a higher rate.
Correct, yes. So then when you have a home charger, you could have potentially a 20 kilowatt charger at your home. Then it comes down to how much you're spending on your connection to the grid.
Yeah. I think particularly people with two cars, there might be one that stays at home, one that goes to work.
Yeah.
And so there'll be the one that doesn't get an opportunity to charge at home very often because it needs a long, slow charge.
Yep.
But having a quick charge occasionally, certainly if you had the capacity to do that's another question.
Yes.
Homes have been built really for just the appliances in your home.
Yes. And then, but then you go to there's the capacity of the home, and then you expand that out to the capacity of the grid, right? And that will be another issue to be addressed about that macro level of managing power flow within the grid.
You might have what's in the UK is called the Coronation Street effect. Do you know about this?
No.
So, Coronation Street, the long-running but now deceased TV series, was widely watched in Britain. And whenever there was an ad break, everyone would go and put on their kettle and make a cup of tea. So there was this very defined moment when the power on the grid would just rocket up. If everyone put on their 1,500 watt kettle.
Yes.
And so in the power stations, they had to kind of watch Coronation Street, waiting for the moment. It's time to crank up the furnace.
There you go. Yes.
So you can see the same thing happening with people, like pigeons coming home to roost, plug their car in when they come home. So there'll be this big peak all at the same time.
Yes.
What's the solution?
One, it depends. There needs to be a signal to people about when it's okay to turn on to charge their car or not, right? And that signal could take many forms. It could be a very explicit signal that says you are allowed to charge at this rate now. It could be a price signal that, at this time, it's now more expensive to charge, and that will act to, smooth out that charging.
So how can you tell a charger to change its rate? How does that happen?
Oh, so that's communication standards that are being developed, and for EV chargers, there's a standard called OCPP, which is to do with that communication between the charger outside world, let's call it, whether that's via the internet or however it is, that's where that's happening.
Right. So I'm just thinking through an equivalent at the moment is in South Australia and Western Australia, they're starting to introduce flexible exports of solar because they've got too much solar. And they're wanting to have more sort of fine-grained control of your home solar power system.
Yes.
I guess the same could be implemented for electric vehicles. So there's a little bit of scheduling going on.
Absolutely.
I mean, I'm just thinking about three-phase, for instance. You could even just do it like, so many minutes on L1, then L2, then L3 on the same LV network. Would that help? No, that's out of balance.
Yeah, no, that wouldn't help at all. That wouldn't help at all.
Let's make them synchronise. Yeah.
Yes.
Yeah.
So no, it's and as you say, all of these things are evolving as essentially this is an acceleration of issues that have been going on in the grid for a while.
Yeah.
Initially, it was solar PV and that distributed energy generation. That was not how our grid was designed and envisaged, and so that was a shift. And then we're transitioning essentially, the way you could think of it is the energy that is in all the petrol that is burnt every day in Australia, we're now expecting to come from our electricity grid.
Yeah.
And so that won't happen overnight, but that obviously the grid will need to change to be able to manage that.
Right. Wow.
Yeah.
I'm just thinking upstream from your home. Next thing is the transformer down the street.
Correct. Yes. And so, I have a friend of mine who wanted to get solar, and he was told, well, you can only have 3 kilowatts because your neighbour's got in first, and the transformer is now full. Oh, not, the transformer's at capacity. If you want to pay us $10,000 to put in a bigger transformer, then you can have 5 kilowatts. But otherwise, you can only have 3 kilowatts. And so you might see things like that happening with EV fast chargers at home. The people who get in first in the street get in first.
I'm thinking on my feet here, but we have two problems at either end of the spectrum. We've got a generation problem with synchronised solar, i.e. it generates with the sun.
Yes.
And then we've got a load which might well come on whenever. If we kind of match those better,
absolutely,
that would be nice, especially in a DER sense. Like, in the same street at the same time, solar's pumping, cars are charging. There's going to be very little load on the transformer, but you'd have to guarantee that to happen. So there'd have to be fine-grained control of that.
Yes.
And maybe with some price signalling.
Maybe price signalling.
Yeah.
But so there's two different. There's a myriad of approaches. At one end, you just say it's a market response and it's price signalling.
Yep.
At the other end, it's a technology response, and the grid operator can tell any piece of equipment when to turn on or off, or how much it's allowed to draw or generate.
That's where AEMO sits at that end.
Well, AEMO actually kind of manage all of it.
Yeah, but they do set the pricing.
Yes, they just yes. So, and that's sort of I develop power conversion equipment.
Yeah.
I have awareness of these topics. I'm not an expert in these topics, but they're interesting to think about in relation to what we're developing.
Yeah, it's technology meets policy.
Correct. Yes. Yeah. Which is where some people say that's where the most interesting stuff is.
Yeah. So I've just got my notes here. Fleets, heavy-duty vehicles, and DC fast charging. What's that about?
So there's a system called MCS, which stands for Megawatt Charging System.
Yeah.
And that is taking EV charging up to that next level. So that's talking about buses, trucks, boats, and planes, and how you can charge much faster. And at those levels, they're talking up to, say, 1,200 volts at 1,000 amps. So, that's 1.2 megawatts. And for that to happen, there's technologies like the actual plug that you are plugging into your vehicle and the cable are all liquid cooled because there's so much current going down that thing that to stop it melting, you need to actively cool the cable and the connector.
I mean, it sounds dangerous, but I like to kind of think about what we've got at the moment with internal combustion engines. Is that you turn up at a service station and you open a hole in the side of your vehicle where combustible fumes are venting out, flammable gases, and you get a pipey thing and hope you get it in the right hole and squeeze, and you just read the instructions that say you should be over 16, don't talk on your mobile phone, don't smoke. And that's all the safety information we get. But when we've got an electrical connection, there's all this kind of communication and preconditions and, like you say, liquid cooling. It's kind of a lot safer.
Yes.
Yeah.
Yes. It is a lot safer.
You can't even drive your car off. Like you can with a service station. You can just drive off and rip the hose off.
The car won't let you. No.
No. In fact, I believe your car sometimes won't let you after you've charged.
Well, yes. So what we're finding with the Nissan Leaf is that when you charge it on DC, I think this applies to some of the earlier versions, and we've looked around on the internet and there's
we should flag it that you've got a direct import from Japan, so it's not what you buy in Australia.
It's not what you buy in Australia. But when you look around on the internet, it seems to be a known problem with some of the earlier ones that when you DC charge them, it causes some communication faults that get logged in the memory of the computer that can sometimes lead it to not want to go.
Euphemistically, brick your car.
Oh, we haven't actually bricked it yet. We've always been able to reset it. But
you've got like, $1,000 box that allows you to reset it.
Allows you to plug into the car's computer and look at all the fault codes and go, I'd just reset that.
Does that come in the boot with your spare tyre?
No, we actually got that separately. That's okay.
Now, when you pulled up here, you plugged into the lovely Delta 50 kilowatt charger. Now, it's an older model, and we did pick that up, and it did take a crane to lift it. It's a 50 kilowatt DC charger, weighs 780 kilos. So, how heavy is your 50 kilowatt charger?
So, our 50 kilowatt charger weighs 50 kilos.
How do you do that?
Using switch mode power conversion technology.
Right. So, the difference is that's got a massive transformer. It's copper and steel.
Well, and when you say mains transformer, the key thing that you need to understand is that's operating at 50 hertz, right? And when you operate a transformer at a higher frequency, it means you can make it smaller.
Right.
That's the key.
That's a bit of magic. Yeah.
Oh, I call it physics.
Physics.
In some ways, they're indistinguishable.
That's right. I think Arthur C. Clarke said that.
Something like that. Any sufficiently advanced technology is indistinguishable from magic.
Yeah.
Yes.
Yeah. It's so true. It's so true. So that's why your 50 kilowatt charger, which we'll have a look at in a moment, the RT22. And what sort of power levels could you go up to with that unit?
So we've designed it. So it's a module. We call it a module, and that can be stacked together up to 350 kilowatts. So an EV charger maker could make a 50 kilowatt charger, 100 kilowatt charger, all the way up to 350 kilowatts just by choosing the number of modules that they choose to put inside their equipment.
And what, up to 1,000 volts?
1,000 volts, yes.
Oh, wow.
Yes.
Okay.
And that's to go with some of the different vehicle standards around the battery voltages. And again, that's another one where it's not necessarily clear what the answer is going to be. Different makers currently are doing different things.
Yeah.
Some, the battery nominal voltage is 800 volts. So that'll be a bit higher when it gets to full charge.
I see that trend happening now. So, like our EV, which is a couple of years old, is 400 volts.
Yes.
Most of the ones here are.
Yep.
But the new Ioniqs and I think the Teslas are 800 volts.
Yes, I think the Porsches are 800 volts as well.
So for those who are not familiar with Ohm's law, you double the voltage, you halve the current.
Yes.
And current's your problem. It's the size of your cable and the heat and all your electronics have to carry that. But the voltage is a kind of a bit of a friend.
In terms of the transmission of the power, it's a lot easier to do at high voltage.
Yeah.
I'm sure the people who are designing the battery packs, they've got their interesting challenges to solve as they scale the battery voltage up.
Yeah.
Because when we talk about the car battery, it's not one 800 volt battery. No. It's a whole lot of smaller cells stacked on top of each other.
It's amazing to think that an 18650 cell like the Tesla started with, just 11,000 or something of them, all stacked in the bottom of your car.
Yes, that's right.
Luckily, you don't have to take them out one by one and charge them.
There's a very funny video somewhere on the internet about a Mercedes where you actually open the fuel flap and you pull a little thing, and then all these AA batteries start, like thousands of AA batteries start coming out the side.
Now, we've got charging from the grid to the vehicle, but what about reversing that process? I get a lot of questions like, when will I run my house off my electric vehicle's battery?
Yeah, so that's called V to G, or vehicle to grid. Some people call it V to X because there's other people think about it in other ways, vehicle to home, different ways. But essentially what it means is that you're taking energy out of the battery, and you are putting that back into the grid to power either your home or whatever, the grid really. And so people may be familiar with a stationary home battery system where they've got a backup battery maybe connected to their solar system. Really, this is no different to that. The only difference now is that the battery is on wheels. And what has to facilitate that, there needs to be communications protocols that are being developed. And there's a standard called ISO 15118-20, which is a communications protocol standard.
Now, why do you need a communication protocol?
It's because the reason you need a communications protocol is because you've got different cars made by different manufacturers, you've got different EV charging equipment made by different manufacturers, and so we need a recognised language for all of those things to talk to each other.
So it's kind of the USB of car charging. So
correct.
Anything can plug into anything with the right connector on it.
And so that there's the messages are understood where the EVSE says, I want to take 10 kilowatts from this battery to put into the house. It can explain that to the car. The car can say, okay, I'll accept that at this time, or no, my battery is nearly flat, I'm not going to let you do that at this time.
I've heard some pundits say how useful it would be for many people who the vehicle leaves and there's still loads in the house. So really, it's only when the vehicle's at home that would be useful. And where do you charge it? So if you're going to charge it at home, you're not going to use it as your power supply.
I mean, it's one of those things that's evolving, and I don't think all the economics have played out yet.
Yeah.
I have heard of cases where people have just gone and bought an EV that has this capability and put it in their garage as their home battery because it's the cheapest way to buy a big battery.
It is.
Right?
Look, I've got a 60 kilowatt hour battery pack here for my microgrid.
Yes.
And it costs about the same as my car, which is a car and a 64 kilowatt hour battery.
Exactly.
So I get a free car.
Free car with your battery. There you go. So that, but clearly that won't. That only is happening because of sort of the markets and volumes and things like that.
Yeah.
It makes no logical sense.
We're starting to see cars come out with power outlets on them, so vehicle to load. So you actually got a 3-pin plug on your car, and you can. I mean, some of them have like 6 or 7 of them. Yeah, it's not going to ruin your weekend. It's going to make your weekend.
That's right.
You take your induction cooker with you, and your small portable fridge, and all your toys.
You just need to make sure you've got enough to drive home.
That's right.
But it does. I mean, I see this as part of a trend, which I didn't make this up, but it's the electrification of everything.
Yes.
It's your home water heater is now a reverse cycle heat pump. All of those, your cooking is an induction cooktop. It's the electrification of everything because it is. You can have very fine control of the power. We have the technologies to make it safe, and when the energy sources are renewable, well, then everything's renewable.
Yeah.
And so to me, we're at the start of just a trend in that direction.
Maybe I'm trying to think of another analogy. I love an analogy. So electricity is the Bitcoin of energy. It can be traded anywhere, anytime.
It can be traded anywhere, yes.
It's very flexible. Hopefully it doesn't have dive.
and people are using it to speculate as well.
Yeah.
There are power companies that essentially encourage you to buy your power 3 to 6 months in advance, and they say, we give you a bit of a discount. If you buy it now for November, you get a bit of a discount, and essentially they're just running a hedge fund about what they'll be able to buy it for in the future and what they can charge you for it now.
All right, that helps fund their ongoing
that's
growth.
Right.
Yeah,
that's right. So it is becoming it's a commodity.
So coming back to bi-directional charging, because there's a lot of interest in this.
Yes.
Are there any products you can buy now that do this, that you can install in Australia?
So the first thing, you have to start with the car.
Right.
The car. The car has to allow it. Right. And I'm not actually. I don't want to say anything because I don't actually know about who has it or doesn't.
I'm pretty sure it's only CHAdeMO.
Yes.
Yeah.
And so I think that means that maybe Mitsubishi have an offering, and
Nissan
and
the Zoe.
Right. Okay.
Because they have the CHAdeMO.
They've got
ports.
Yes.
Yeah, and that's because they have
you
the
can
communication
you
protocol.
can have CHAdeMO cars that still don't allow the bi-directional.
Right.
Okay.
Yes.
It's not just because it's CHAdeMO that it can be bi-directional. The CHAdeMO standard has everything in it to enable it.
Yeah.
But that doesn't necessarily mean just because the car maker's putting a CHAdeMO badge on their car that the car can do bi-directional power transfer.
Yeah. Rather than us making up rubbish, let's reach out to the hive mind.
Yeah.
If anyone out there actually knows, put it in the comments, please.
Yes, there you go.
But
so you've got to start with the car.
Got it.
Right.
Yeah.
And then once you've got the car, then the however that connection is being made to the grid, whether that's an AC connection or it's a DC connection, the equipment has to have the capability to communicate with the car that it can take power back to the grid.
Are you saying that you can get bidirectional AC out of the car to the grid? I thought it was always DC.
in the AS4777 standard, which is historically everyone thinks about that in terms of solar inverters, because that's where it sort of came from.
Yes.
In the most recent edition of that standard, it allows for so the title of AS4777 is grid connection of energy systems via inverters. Right, so it's not saying it's PV. It's not saying what the energy source is. It's just saying when you connect an energy source to the grid with an inverter, this standard applies. Now, so when we think about it in that context, in the latest edition of it, it allows for the energy source being an electric vehicle, and it doesn't stipulate whether the conversion from DC to AC happens in a box on the wall or in the onboard charger in the car. So the power in the cable can be either AC or DC.
Okay.
It doesn't matter. It's allowed for in the standard. And that is, again, perhaps one of the difficulties for people who want this to happen now, and why it hasn't happened now is because it creates that uncertainty about what's the best way to do it. Which way should we do it?
So we're interfacing with a utilities network, so we've got to play by the rules.
Play by the rules, and that's what the AS4777 sets the rules for the equipment.
Yeah, gotcha.
Right?
Yeah. It's about safety and grid stability, really.
Yes, and that grid stability. And that was the reason for the latest edition, because there is now so much PV in Australia that it is affecting like the whole electricity, the whole NEM could be affected by what's happening with inverters on people's walls. Yes.
People often think it's about the energy they export to the grid, but it's actually the hidden load as well.
Yes.
That you've basically, when you're generating your own energy and using it, and if something was to change on the network and all those inverters turn off together, whoa. We've got 13 gigawatts of rooftop solar. If that turned off, it's lights out Australia.
Yeah, so it's almost the equivalent of someone unplugging Loy Yang. Right?
Yeah.
Straight away. That's the people who are responsible for thinking about that. It's AEMO, and so that's why they got heavily involved in the latest revision of that standard.
Yeah, they're having a lot of sleepless nights at the moment.
Yes. I'm sure they are.
They think of everything. Apparently they're worried about a total eclipse in Queensland. I think it's 2028.
Right.
Because that'll be lights out in parts of Queensland for some minutes.
Yes.
Yeah. So I noticed you've mentioned onboard charging bidirectional with Renault, BYD and Hyundai. So those currently have that functionality, but it's not necessarily compliant with our grid standard.
Well, so what that then means is the car maker has to get to be able to offer that in Australia. They have to get that onboard charger qualified to be compliant with our Australian AS4777 standard. In other parts of the world, it's a different standard. So in the US, it's called IEEE 1547. Right, and in Europe, the German one's called a VDE AR4 something.
Yeah, I'll put it down there.
But the key is that there's different standards all around the world, and so to be able to offer that bidirectionality in a particular market, the onboard charger has to comply with the standard in that market. And Australia being a small market, and all of that comes with a cost. It's a development cost, it's a qualification cost, it's a validation cost, so then it comes down to the size of the market. Australia is not a very big market for EVs.
No. And we haven't got the incentives.
And we we could have a whole other discussion around why that is.
Yeah.
But so they probably haven't put the investment into making that available yet in Australia.
Here's an edge case for why vehicle to load can be useful. One of the people that live here, so this is an off-grid community, is about to buy a BYD Atto 3, which has a socket outlet.
Yep.
He's just asked about if he charges his car up at the sort of local community charging area, can he bring it home and then charge his home power system off it?
Legally, no. Because you're not allowed to. Oh no, charging it. Maybe he can. Yes, he probably. I don't know.
Again, there's a grey area.
Maybe I don't really
there's a grey
want to
area
talk
about that
to
coupling because if it's an interactive inverter, the male pins could be live.
Could be live.
But if it's a rectifier, it's just basically a input.
And so if the piece of equipment that charged the battery was a unidirectional piece of equipment, then he could do that.
Yeah, right.
He would need to seek guidance from a qualified
That's a good
person,
and
like an electrician who's not me.
Either.
Who's not me. That's right. Yes.
But this is interesting. With the idea of shifting energy with your vehicle. That's what I'm getting at.
Well, it's like for people who aren't connected to mains water.
Yeah.
Sometimes they have to ring up a truck to come and fill up their dam or tank.
Yeah, been there.
It's exactly analogous to that.
Yep. People get those kind of old plastic tanks that used to have Coca-Cola in them.
Yeah.
Put them on a trailer and drive to a filling station.
And so, in relation to the EVs, I was in May. I was at a trade show in Germany, very big, and I saw a stand where what their business model that they were offering was, you imagine your RACV ring up for a replacement battery. Yeah. This van had a big battery in the back and it would drive up and recharge your electric vehicle wherever you were.
Ooh, that's kind of useful. That's going to be needed. Because when you go to turtle mode and it turtles out,
that's right.
You're stuck. It's basically put on the back of a truck and drive it away.
Yeah.
Yeah, right.
Or you ring up these people and they'll come and just plug in and charge you up.
Wow. It beats carrying a little portable generator in the back and sitting for 2 hours waiting for it to charge your car.
That's right. And so, again, it just comes down to, I think it's highly likely we'll see that in Australia. Yeah. It just comes down to when there's enough people to make it a viable business model.
Wow. Okay.
Yeah.
And would they be doing a AC to DC conversion, or would it be DC?
I think that'd just be to DC to DC.
Okay.
Well, so in this case, it's a battery in the van, the battery in the, a battery in your car. So you would just do DC to DC.
Right.
I mean, power conversion engineers can do anything. We could convert it to AC and then back to DC.
Yeah.
But why?
Just for the hell of it.
Yeah.
Yeah, right. It's just a few efficiency losses along the way.
Yes.
Now, we're coming to the end here of my list, and I see that I think we've started this already about whether the grid can cope with the rush to, full EVs.
Yeah.
What's your opinion?
I think it will.
Yep.
You know, the drive will be there. So I think people, a thing that I think people don't quite appreciate is that they think Australia can make decisions on our own, right? We don't make any cars anymore, right? All the car makers in the world are being pushed by the really big markets who are saying, the UK and Europe are saying things like, there's a law by 2035 or whatever it is for their different market, you will not be able to buy a petrol-powered car or an internal combustion engine car anymore. So what's going to happen is that the number of those cars that are made in the world will decrease, so their price will go up. The number of EVs in the world is going to increase, so their price will come down. And if Australia isn't in a position to be able to buy lower-cost EV cars, we're going to be left only able to buy more expensive internal combustion engine cars. So to me, it's inevitable that, it's not a price taker, we're a product taker in Australia for vehicles because we don't make them anymore. So we can either pay that cost and let it take a lot longer, or we can sort of embrace it and recognise that that's what's going to happen and make the transition as smoothly as we can.
Maybe it's the opportunity for the rebirth of the Australian manufactured vehicle.
Well, there are people who are talking about that.
People are doing it right now.
Yeah.
There's Australian-made EVs.
Yes, and certainly we're also for trucks and that sort of thing. I mean, I've seen proposals for people to say, Australia's got the lithium, we should be making the batteries. Let's put a massive battery factory here in Australia.
That's starting.
Yeah.
There's a couple of startups looking at that now.
Yeah.
But I'm just thinking about the difference between an internal combustion engine manufacturing and an electric vehicle. Electric vehicle has about, a dozen moving parts. So
Correct.
there's very few moving parts.
Yes.
It's basically mouldings, bodies, batteries, and an electric motor and some control systems.
Yes. So as a mechanical engineering exercise, it is much, much simpler than an internal combustion engine.
It's rocket science building engines.
But in terms of the electronics in it, it's it's a computer.
Yeah.
And that's happening in petrol powered cars anyway. The whole car's computerized. And then you've also got that core of power electronics. So it's not just the power electronics to charge the battery, it's to take the energy from the battery and turn the motors. All of that is power electronics. So essentially our battery charger that takes AC and turns it into DC to charge the battery, there's the opposite. There's an inverter that's taking the battery DC voltage, converting that back to AC to power the motors. Spin the motors.
A very specific kind of AC.
Yes. I mean, and that's the thing. It's all about optimising the inverter and the motor so that they can function together as a system.
Yeah.
So essentially, previously, where the internal combustion engine was a thermomechanical piece of equipment, now we've got an electromechanical piece of equipment that is the inverter and the motor operating together.
Yeah.
And so that's in some ways a lot more sophisticated than an internal combustion engine. But given the supply chains, it can be easier to manufacture, or the manufacture of it is a bit more distributed.
Yeah.
All those things.
Yeah, I think I like what you said about it's inevitable because of governments are putting limits on when you can sell an internal combustion engine. I think of this photo, you've probably seen it, dating back to the beginning of the 19th century in New York.
Oh, yes.
And
yes.
I'll put it on the screen, but it's a picture of New York where a big street where it's all horse and carts, and there's one car. Petrol-powered car.
Yep.
And then only a matter of a few years later, it's all petrol-powered cars and one horse.
Yes.
And it wasn't just that change, it was the whole infrastructure that supported the horse-driven industry disappeared. So the liveries, for instance, you had to have somewhere to water your horse and stuff. That all disappeared in a matter of a few years. and it was replaced with centralised pumping, and that took a while too.
Yes.
They had the same problem. There wasn't very places to fill up your petrol car.
Exactly. Yes. Or like,
but it happened quickly.
It happened quickly.
Yeah.
Yes. And I haven't, and I don't actually necessarily think that EV or battery EVs, as we currently are, they're currently being developed at the end either. I mean, I have an analogy. So in my lifetime, I've seen in the audio music sphere, I've seen LPs, cassettes, CDs, digital storage,
streaming,
and now streaming, right?
Yeah.
And that's in my lifetime,
yeah.
Right? So the amount of infrastructure around cars is greater, and so I'm not saying it's going to happen as quickly, but in my head, I wouldn't be surprised that battery EVs are a stepping stone to something else.
Whoa, what would that be?
Well, certainly for trucks, people are seeing hydrogen fuel cells as a more viable.
Right, because energy dense.
It's more that your capacity is not as constrained by, you can put a bigger tank on and get more range, if you like, right? It's a bit hard to just plug a bigger battery in the car. It's more... It's
you could have long-range vehicles, short-range vehicles, which is just a matter of plugging in that extra tank.
And even a step further, you think about a diesel train.
Yeah.
Okay, we can electrify all the lines, or we could have something with a different energy source.
Right. And hydrogen being possible to make from electricity as well means it's part of that system.
Part of that
system. We don't have to dig it up out of the ground or pump it out.
Yes.
We're just basically taking sunlight, wind, and water and turning it into an energy source that can be converted to lots of other things.
Yes.
It's fantastic.
And then back to water.
Oh, God, I've got all goosebumps. Electricity's so good.
It is.
Except when you touch it.
Yes, don't touch it.
Hey, I think it's time to look at the RT22.
Okay,
what do you reckon?
Right. That'd be fantastic.
Shall we get it out?
Yeah,
cool.
Let's do it.
All right. So, Peter, the RT22.
The RT22.
It's in a cardboard box.
That's right.
I love cardboard.
It's good.
Cardboard's good. More cardboard.
More cardboard. Only cardboard.
Not lots of unrecyclable foam.
No, all cardboard.
You're kidding. That's so nice.
It is. It is good. And there it is. Now, what you can also do is just fold that end out. Oh, this one folds out.
Yep.
And then we can pull it and just pull that towards you.
Yep.
Here we go.
Right. Just put it down the shop. Cut that bit. I really like the packaging, by the way.
Yeah. I mean, there was a first attempt where it did have non-recyclable foam, but they've done a really good job, I think.
Wow. Now, look, we better fess up. This is a dummy unit.
Correct.
It's 50 kilos and it looks the same.
Correct. It looks the same, but as you can see, we're hefting it around. It's not 50 kilos.
Yeah, right.
Yes.
So it's next to useless for me.
Yeah. Yes.
But listen to the basics. This looks like your standard rack mounting design.
Exactly.
So it's 4RU?
Yes, that's right.
Yeah.
Yep.
And it's got mounting points here.
The ears on the side.
Yep.
So the idea is it'll slide into a shelf, and if we turn it around and have a look at the back, that's where this connector system comes in. So the rack would have a back panel in it that has the mating connectors here. This is the AC input. You can see the earth pin there's the slightly longer one, so it's the first mate, last break concept. And this is the DC up here, and there's that. This is a particular connector that's got those high-powered DC connections, as well as the communication signals in there. And so that just slides in and mates into the rack.
Is it like hot swappable?
It is hot swappable, yes.
Whoa, okay. Because of these communication pins, they break and turns off, or
yes, yeah. There's a we call it an RIP, rectifier in place pin.
Yeah.
And if that signal is broken, then it'll disconnect. And we've got internal protections that mean that you're not having an inrush into the output capacitors in here from the bus that you're connecting to.
All right, so from a field service point of view, it's not electrical work to disconnect this. You're turning, you wouldn't take it off load ideally, wouldn't you?
If I was doing it, I'd be shutting the system down
Yep.
and up. But conceptually, this could be hot plugged. Yes.
Right, but there's no terminals that you have to connect
No.
to wires, potential
No.
hazards, it's
No.
all screened. Right.
It's all part of that's done wherever the rack is manufactured, put together.
All right,
Yeah.
wow. And you can put up to 350 kilowatts, so what's that, seven of them?
Seven of them, yeah.
Wow. The limiting factor is what?
What that would limit would be your rack side equipment. From this side, there's really no.
You've got 125 amps coming out of here, right?
Yeah.
And so times 7.
So the limitation, times 7. Well, no. But each of these connectors only sees 125 amps.
Yes, but I'm saying it goes onto a backplane.
It goes onto a backplane.
And it's summing it because they're in parallel.
Yes.
Yeah.
Yeah.
Okay.
So it's the limitation on the backplane.
Yep.
In terms of the control systems within this, essentially they are just a current source.
So it's nearly 900 amps on the backplane.
Yeah.
Whoa.
That
might be your limiting factor.
Yes.
How big those bus bars are.
But it's not necessarily an inherent limit of the
unit
itself. Yeah.
Wow. What about can you have parallel units? So you've got 350 kilowatts, etc.
Well, you can, but it goes to then the control to the load.
Yeah.
Like whatever you've got to have a connector that can take all of that power if you're putting it all into one load.
Yeah, I'm just trying to think what we wouldn't need. There's no chargers that could take more than 350.
No.
I think at the moment, but
No.
right.
Yeah.
Now,
but this is where this megawatt charging system that we're on a committee that's discussing what that is going to entail, and they're thinking about those kind of issues at the moment.
Now, because my legs are squished here, let's put this back on the table.
Sure.
And we can talk a bit more about it.
Yep.
Okay.
No problem.
Well, Peter, here we are with the RT22 on the table, unboxed out of that beautiful cardboard packaging.
Yes.
You told me just while we were off camera that that was, a decision about the whole manufacturing process from beginning to end and to minimising waste.
Yeah. So that evolved. That packaging evolved. There were some original embodiments that had. Non-disposable, non-recyclable packaging, but I think it's a good decision that the company's made to go with that solution.
Yeah, I call it engineered cardboard. You just think about it like an engineer. How do you make volume?
It's amazing what you can do with cardboard.
Yeah,
it's really incredible what you can do with cardboard.
And I think. You originally from Christchurch? No. I thought there was some connection with New Zealand, but they after the Christchurch earthquake, they rebuilt one of the churches out of paper.
Paper.
Yep.
Wow.
So they used engineered cardboard.
Yeah. Wow.
Because people were a bit nervous about being in buildings for a while there.
Yes, I can imagine.
Yeah. It was a Japanese architect who designed it, and it was all tubular constructed engineered cardboard. But anyway, we're not talking about cardboard.
No.
We're talking about this.
Yes.
We know it's 50 kilowatts. We know that it can do 50 volts to 1,000 volts.
Yep.
Whew, it's a huge range. 125 amps. We can stack them up to 7 high, which gives us 350 kilowatts. I noticed it's got 3 big fans on the front.
Yes.
What's that for?
So, even though it's a high efficiency unit, it still has to dissipate a couple of kilowatts of power. And so that's what the fans are there to stop it getting too hot.
Which way does it vent?
It's inlet at the front, outlet at the back.
Right.
Yes.
Yep. So the cabinets that these go into aren't your cabinets. These are your components for someone else's product.
Yeah, so essentially this is a component for someone else's product. And they can take we've designed it with that in mind to enable them to make an effective charger. but it's up to them to make the rack at the back and how it all interconnects. The other equipment that is required to have in an electric vehicle charger to manage safety and those sorts of things. Yeah.
It parallels the automotive industry, which is lots of component manufacturers make bits that all go into a vehicle at the end.
And so similarly inside this, there's circuit boards with a whole lot of components that we didn't make.
Yes.
We're just building it up to the next level, and then there's someone after us building it up to the next level.
So how have you got on with the so-called chip shortage?
It's been a real challenge, yes. I wouldn't call it so-called. No. I'd call it actual. And the big things are this is a digitally controlled product, so it has a DSP in it. They've been very hard to get, and they're particularly a component. As makers of equipment like this, we like to try and design it so that all the parts we can buy from different suppliers, and that minimises our risk. The DSP that does the digital control is not one of those parts, and so that's created a big headache for us. One of the enabling technologies within this box is silicon carbide MOSFETs. They're a relatively new technology in power transistors, and they're being heavily pushed to everything EV, and because they're relatively new, there hasn't been so long for the makers to scale up their production capacity, and so there's a lot of interest in EV charging equipment and EV charging, which is creating a huge demand for silicon carbide MOSFETs, and so we designed our product using one from a particular manufacturer. We're now redesigning our product to use one from a different manufacturer, so essentially qualifying a different part in it,
right?
Just because we can't get the ones from the first manufacturer.
Let me ask a bit of a dumb question. So I'm familiar with IGBTs, integrated gate bipolar transistors.
Correct.
Yep.
Yes.
Which are often used in high-powered switching.
Yes.
So silicon carbide, is that still IGBT? But
no. So after IGBTs, there came MOSFETs, metal oxide silicon field effect transistors, and they're all silicon. And then there's now evolutions of those types of devices using silicon carbide or gallium nitride. Are the two sort of, I won't quite say competing, but they're new technologies in those power semiconductors.
What makes them so good?
Well, essentially, your ideal switch would have zero losses when it's turned on, and the transition between on and off would be completely lossless as well. It would happen instantaneously. It would go from on to off. In reality, when you turn a MOSFET on, there's a tiny little resistor still. It's got a resistance, and so a better MOSFET has a lower resistance, and also can switch more quickly. And silicon carbide enables, particularly at high voltages, enables that low resistance with fast switching with a high withstand voltage, and that silicon carbide is enabling better switches because of those characteristics.
And they can operate at high voltages. Yes.
So the most common voltage for silicon carbide MOSFET is 1200 volts. The sweet spot for silicon MOSFETs, I would have said, was 650 volts or below. IGBTs can be made up to thousands of volts. It's just different characteristics of the different devices.
Right.
Yeah.
Now, you mentioned gallium nitride?
Gallium nitride, yes.
So how does that fit into the mix?
So gallium nitride is another new switch technology. It seems to be finding its application more in lower powered chargers, like maybe your mobile phone charger or chargers up to a few hundred watts or a kilowatt. Seems to be where the uses for those are at the moment. But again, they're very low on resistance and very fast switching devices.
Right.
Yeah.
Well, so this has got state-of-the-art switching built into it then?
Yes, that's right.
Wow. That's great to hear. So,
Yes.
And it's an Australian-developed product?
Yes, all the development was done at our offices in Burwood.
Were you involved in that?
Not initially. I've been involved in it for about the last 6 to 12 months.
Right.
Yes.
So this is kind of your baby?
A bit, yes. Yes. Not from conception, but, in the delivery, let's say.
Yeah. Maybe one day you'll have one at home.
Maybe.
And you have to run a little cord up through the trees and drop it down into the street where you're parked.
Yes, maybe. We'll see.
350 kilowatt cable.
Yeah. Big fat cable.
Yeah.
So yeah, it's been a challenging project. There were challenges through when people couldn't be in the office working together through COVID, through the supply chain ructions that have happened since then has made getting components hard. But we've got some solid interest from a few customers, and it's going well.
It's great to see the onshoring revolution happening.
Yes.
Make it here, design it here.
Yes.
Get as many of the components as you can here.
Yeah.
But we know it's a global market for a lot of those things like that DSP. But wow, well done.
Thank you. Yeah, it's good.
Well, thanks for coming, Peter, and let's hope we get you home.
Well, thanks for the charge from your fast charger out the front. It's been great. I've got high confidence I'll be able to get home.
And it is downhill to start
And
with.
it's downhill. That's right. No worries. But yeah, thanks very much for having us, Glenn. It's been great.